Okay, section 4.8, analyzing graphs of polynomial functions. Okay, this actually ties this chapter back to our very first section, section 4.1. In section 4.1, we were looking at the graphs of polynomial functions, but we were basically just graphing them by plotting points, looking at our calculator, so forth and so on. In this section, we're going to expand what we're looking at in the graph. We're going to go back and talk about domain and range, increasing, decreasing, maximums, minimums, and things like that. So our objective is going to be able to use the x-intercepts to graph a polynomial function, use the location principle to identify zeros of polynomial functions. So we'll learn about a new, actually it's kind of a theorem called the location principle. Okay, find turning points. We haven't really called them turning points before, but we'll talk about these turning points, and identify local maximums and local minimums of graphs, and identify even and odd functions. That's a new idea as well. We're going to talk about, just like a number can be even or odd, a function can be even or odd. Okay, all right. So first, let's review some things we know about polynomial functions. First of all, a polynomial function, again, is of the form a times x to the n plus b times x to the n minus 1 plus c times x to the n minus 2 ... and so forth until we get to our constant z down here at the end. So basically it's numbers, it's these monomials, these numbers times powers of x, okay, and then the sum of them, okay, and our powers of x are always whole numbers here. Okay. And so what we've been doing is we've been factoring them, solving them, so forth and so on, and we're going to look at how those all relate to each other. Okay, first of all, we found zeros of the function, and again what a zero is again a zero that makes this function equal to 0. So it's the number that you put in that gives you out a 0. Okay. So if, let's say, we have a number 6 is a 0 of the function, well then we know that at one point we had a factor of x minus 6. X minus 6 was a factor, okay, because that factor gave us this as a 0. Okay, and we also call that not only a 0, but we also call it a solution. A solution to the equation f of x equals 0. What is that function equal to 0? So we call it a solution, or we call it a root. Those all mean the same thing. A 0, a solution, a root, they're all meaning the same thing. Okay, and if this 0, okay, if it's a real number, again, some of our zeros weren't real. If it's a real number, like in this case 6, okay, then it's also an x-intercept. Then it's an x-intercept. And many of us are very good at finding those x-intercepts in our calculator. Okay, we rely on that a lot. Okay, which is fine, but we need other methods as well, okay? Because that only works, using our x-intercepts only works if it's real. If it's an imaginary, for example, 4i, like our imaginaries 4i, we're not going to see that. A 0 like this, if this is a 0, won't show up on a graph. Won't show up on the graph. Okay, so we need some other methods, and that's where like our p's over q's came in, and our synthetic division, and so forth and so on, to find those other zeros. Okay, so we're going to use that idea of those zeros to help us graph these functions. We don't need to go straight to our graphing calculator every time when it asks us to graph it. Okay, sometimes it's way faster to come up with a few points without. Okay, so here they're asking us to graph this function f of x equals 1 over 6. This is times x plus 3 times x minus 2. Okay, so this is already in factored form. It's in factored form. Okay, so here I have two factors. I've got this factor, and then I've got this one here. So if x plus 3 is a factor, then x equals negative 3 is a 0. And since it's real, that tells me it's also an x-intercept. So I know this is going to have an x-intercept at x is 3, so negative 3. So I can come over here, x is negative 3, put it on. I know that's going to be a point on my graph. Okay, because it's a 0 of this function, it's real, so that makes it a x-intercept. Okay, now this x minus 2 is a factor, so that tells me x equals 2 is a 0. And since it's real, that tells me it's also an x-intercept. So we come over here in 2. But even more so, it has this squared there, tells me that that guy happens twice. We have x minus 2 times x minus 2, which tells me that this solution has a multiplicity of 2, which means it's going to bounce off my axis there. So this is actually going to do some bouncing. It's either going to bounce up like that, come up and do a bounce like that, or it's going to bounce down like that. Okay, and so we know all of that without ever having even looked at the graph of this. Okay, so now to get a few other points, I'm going to speed things up by looking at the graph. Okay, and then I'm going to actually show you, I know many of you are pretty good with doing stuff in your graph, but I'm going to show you some tips and tricks using our table. I haven't showed you, I believe, much in the table. Okay, so there I graphed it. We have 1/6 x plus 3 times x minus 2 squared. Okay, let's go and let's look at the graph. Like that. There's my intercepts. Yep, it goes through that negative 3, comes down and bounces off. Okay, so to get me some more points to graph, I could trace. Okay, but another way is it will actually generate for me, it will actually create an XY table. So if you remember, we had our x, or like x f of x, which again, that's our y table. I can actually create a table similar to that in my calculator. Okay, it's this option here. See there above graph, it says table. So to get to that, I need to hit the blue button first. So we go blue, graph. Okay, and here, and depending on how your table is set, mine counts by ones, and I can arrow up to get negatives, arrow down to get positives. Okay, but you can change what your table does by changing the table settings. If you notice here, table set, that's your table settings right above window, and I can get to that by hitting second window, and I can go, this tells me my table start. Where do I want it to start? Like if I hit 5, and then this, my delta table, is how do I want my table to count? I can start at 5 and count by tens. Now if I go back to my table, second graph, come on graph. Do you see here it starts by 5s and it goes by up by 10 each time? Okay, so I set that up in that table settings. Okay, or I could even, this is what I love the most, is I can have my independent variable, which that's your x. I can set it up to where it'll ask me. Arrow over to ask, hit enter. And then let's now go back to our table, second graph. You notice there's nothing in it. It's waiting for me to tell it what to graph. So I can just like type in 2. When I type in a 2, I get 0. And we knew that was a point, 2, 0. Okay, 3, 0.31. So I can actually come in and be like, okay, we have the 0.31. So we'll graph the 0.3, 2, 1, 2, 3, 1. And graph that point. Okay, and then what about 1? 1, oh, that's not pretty. 0, 2. 0.02. Okay, we could do 1. It was the 0.1 and 0.6. 1.6 would put me right about, I don't know, maybe here. Okay, sorry, 1.6. We could do some negatives. Negative 1 is 3. Okay, negative 2 is 2.6. See here, I can create this table to get an idea on what this graph looks like and get these points just by using my calculator. So we can come in, and this graph is going to look like that. And I can get all kinds of points using that table function. Okay. So this leads us to our location principle. Really, this location principle is kind of an idea. I call it kind of a bit of a no-duh idea. But if I have a polynomial function, and I have two numbers a and b, okay, so I'm just going to pick two numbers. Here, let's call this number a, put it on my graph, there's a, and let's put b up here, okay? And let's say f of a is less than 0. Less than 0 is the mathematical way of just saying negative. My f of a, meaning when I put a into my function, I get some point down here that's negative. So let's say there's my point right there. So that's my negative. There's my f of a, my negative point down there. And f of b is positive. So when I put a b in, I get some positive number here. So I have some function that has this point here and this point here. Basically what the location principle tells me is that there was a 0 somewhere in between a and b. At some point in between a and b, this thing had to cross that x-axis at some point in there. Okay? So how this can be useful is we can actually use our table, okay, and this location principle idea to help us find all our real zeros. Okay, so here let's look at this one. It says find all real zeros of this polynomial function. So we have a bunch of methods. I'm going to start by just looking at the graph. 6x to the third plus 5x squared. Oh, what happened there? Minus 17x minus 6. Okay. So I'm going to start by looking at the graph. Okay. So really what the location principle is telling me is here at some point in this graph, and if I trace, here we'll go 0. If we notice here at like 1, I'm at some negative 12. But at 2, if I type in a 2, I'm up here at 28. And we can see those same things on my graph. 0, 1, 2. If you see here at 1, I'm at negative 12. If at 2, I'm at positive 28. So I went from negative to positive, which tells me there was a 0 somewhere in between 1 and 2. Okay, so I know there was a 0 in between 1 or 2. So if I was to create a table here, my f of x table, and this is always a good idea, even if you're using your calculator to help you find these points, to still write them down. 0 is negative 6, 1 is negative 12, 2 is 28. So since we went from negative to positive, that tells me that somewhere in between 1 and 2 here there is a 0. We don't really know where, but somewhere in between 1 and 2 there is a 0. Okay, so we could start trying random numbers in between 1 and 2. We also could kind of do a P over Q idea. And look for numbers in between 1 and 2. So if we did P over Q, we'd have 1 over 1, 1 over 2, okay, 1 over 3, 1 over 6. So we could try all of those, 1/2, 1/3, 1/6. So we can go 1/2, nope, 1/3, nope, 1/6, nope. And then we could go 2, 2 over 1, 2 over 2, which is 1, 2 over 3, 2 over 6. Do you see how I'm just able to type those in and see if I get a 0 in my table? 3 over 1, we can just type it in that way, 3 over 1, 3 over 2. Oh. Oop, 3 over 2 worked. Okay, so 3 over 2 was a 0. So 3 over 2 worked. So x equals 3 over 2 is a 0. Okay, so now I'm going to synthetically divide this by 3 over 2. So you have 6x to the third plus 5x squared. Okay, bring down the 6. I'm going to use my calculator to help me with this. So we'll take 6 times 3 over 2. Gives me 9. We need to add that to 5. Gives me 14. Multiply that by 3 over 2. Gives me 21. Add that to negative 17. We get 4. 4 times 3 over 2 gives me 6. We get 0. Okay. So now what's left, since this was x to the third, this one now is x to the second. Okay, so we had one factor, which would be x minus 3/2. And then here's our other factor, equals 0. So now I just need to solve this guy. Okay, I guess a bunch of different methods. One is factoring. I can factor a 2 out. Okay, and then factor it from there. So this is going to factor into 3x and x, and I think it's going to be 2 and 1. So 3x squared plus 6 plus 1. Yep. So 3x plus 1 equals 0. Ooh, kind of tiny here. Subtract the 1 over, divide by 3, so negative 1/3. And x equals negative 2. And so we can try those, negative 1/3. Go back to our table, negative 1/3. Yep, that was a 0. Negative 2. That was a 0. Oh. Okay, so we found all the zeros. So 3/2, negative 1/3, and negative 2. There's our solution set. Okay, those were our zeros. Okay, next page to be continued.